All right, this is the Nature of Science video on the scientific method. So the first thing that we started off by learning about theory versus law. So it's scientific law is a description of an observed phenomenon and tries to predict what will happen. And a scientific theory is an explanation of an observed phenomenon and tries to explain why something happens. So if we looked at the orbit of the planet, the Greeks thought that the planets orbited around an Earth in epicycles. Copernicus theorized a heliocentric model, and Kepler came up with the 3 laws that predict planets' motions, but was wrong about the why. So there is a slight difference. Now, they do help each other, and there is some gray area, but the big key is that a law tries to predict what will happen as a description, but theory is an explanation of why. Now, how many observations does it take for a scientific theory or law to be modified or abandoned? Now, all theories and laws are tentative. So Newton's law of gravity was eventually supplanted by Einstein's general theory of relativity, and all it takes is one observation or one failed prediction to require that a scientific theory or law be modified or abandoned. Now, the orbit of the planet Mercury, Newton's theory could not account for this. So I like this quote up here. It says, it doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. So Galileo came along and he refined like some of the great scholars, and he came up with the scientific method, right, that is sort of built upon. Now, simplified it into steps. So you recognize a problem, you make a hypothesis or an educated guess, make predictions based upon hypothesis, perform experiments to test predictions, and formulate a general rule. So let's just go through an example of this. The first step in the scientific process is to identify something in nature that you want to understand, and then gather as much information about that phenomenon as possible. For example, light travels incredibly fast. The obvious question is, well, how fast is the speed of light? So let's just, now we have to make a hypothesis. Now, a hypothesis is an educated guess to explain and observe phenomenon or fact. Now, here are some attributes of a good hypothesis. A good hypothesis should be stated in the language of mathematics. With mathematical statement, there is no ambiguity. So remember, we talked about saying like, hey, if I want to order a large soft drink, large, ambiguous, right? That could mean a lot of things. But if I said I want a 32-ounce drink, well, there's no ambiguity there. Should explain a wide array of observations related to the phenomenon and should have a test for wrongness. So before the 17th century, there were many hypotheses on the speed of light, but there wasn't much experimental data to back it up. So people thought, some scientists thought that it was like in little packets or that they were waves. And as far back as the ancient Greeks, scientists and scholars all debated whether light even had a measurable speed of light. So Aristotle thought that light traveled at an infinite speed, and other scientific philosophers thought that it wasn't infinite, but really fast and could be measured. Now, Galileo attempted to measure the speed of light using lanterns on the hill. So what he did was he went up on top of the hill, and he had a lantern that was covered up. And on another hill, about a mile away, was his assistant. And they were trying to test, like, hey, when I uncover this, you uncover that, and we can time how fast that. And they tried to account for, the human error with that. But because light travels so fast, like he couldn't quite get a value, right? And he said like, hey, it might be infinite, but if it does have a speed, it's going to be at least 10 times faster than the speed of sound. Now, that was one experiment, and that was a prediction, right? Hey, I can time I should be able to see the lantern, I should be able to time it out. Well, that was a prediction. I should be able to time it. Now we can perform experiments to test the predictions. Now Ole Romer became the first person to measure the speed of light. This was he discovered it by accident because he was measuring the orbital periods of Jupiter's moon Io. So it is known that Io orbits and is eclipsed by Jupiter every 42 hours, and you can see that in those little graphics. Now, by timing these eclipses over many years, Romer noticed something very peculiar. The time between eclipses became shorter as Earth moved closer to Jupiter, and the time between eclipses became longer as Earth moves away from Jupiter. So you can see that diagram down here. The difference was only by 11 minutes shorter or longer than average. Now, Christian Huygens used Romer's data to estimate the speed of light as 211 million meters per second. So this was the first time it was actually observed that light must have a certain speed, and Christian Huygens came along and was able to calculate that. Now, he was off by quite a bit because he didn't really have an accurate like length of the orbit of Earth, right? But he was working with what he had at the time and was actually able to calculate it. Now, this was improved later by a man by Fitzhugh, and he used Galileo's method and a rotating gear to get within 4%. Now this begs the question, though, why isn't the speed of light infinite? So now we have to formulate a general rule. So the speed of light is 299,792,458 meters per second. Now, speed of light is defined as c, as in E equals mc squared. C is the speed of causality. So essentially what this is saying, like in Einstein's theory of special and general relativity, causality means that an effect cannot occur from a cause that is not in the back past of the light cone of that event. Similarly, a cause cannot have an effect outside the front future of the light cone. That's very complicated, but all that means is that it's saying that everything in the universe that has a cause and effect relationship, the cause must always come before the effect, obviously. But the tricky part, right, comes from relativity, is that the cause must always come before the effect for every frame of reference, right? In order for this to be possible, there must be a limit to how fast information can travel in the universe. So no matter how fast you're going, no matter what part of the universe you're in, every cause must come before every effect, no matter what state of reference you're in. And like you're able to calculate the speed limit that would make that possible. And it just so happens that that's the speed of light. Now, nothing with mass can travel at that speed. Anything without mass, like light, will travel at that speed. So the speed limit can be calculated, and it comes out to, well, what we call the speed of light, or speed of causality. So now let's talk about variables. So that's just a little interesting fact about the scientific method. Let's look at variables. So if I'm going to make this claim, the color of light will affect the growth rate of plants. Is this a scientific claim? Why or why not? It is a scientific claim because there is a test for wrongness. We can go out and test this. So let's learn about the different variables in this experiment. So the independent variable is what is being tested. It's the cause, the quantity that you are manipulating. There can only be one independent variable. So if we're looking if the color of light affects plant growth, the independent variable is going to be the light color, right? This is what we are testing. It's what we are testing. The color of light influences plant growth. Now, the dependent variable will depend the response to the changes made to the independent variable. It's what's being measured. There can only be one dependent variable. So if we're looking at the example, does the color of light affect plant growth? What's the dependent variable? The growth rate of the plants. That's what we're measuring. We are changing the light color, the independent variable, to see if it influences the plant growth rate, the dependent variable. Now, constant variables, it's what we keep constant, obviously. Now, if these variables are not kept fixed, it could possibly affect the results, and they usually have many constant variables. So does the color of light affect plant growth? Well, what are some constant variables? Well, the intensity of light, the type of soil, the amount of water the amount of water given to the plant, environmental air temperature, humidity, on and on and on. Everything you want to keep the same except for the dependent or independent variable and dependent variable. So we try to answer this question, well, who's the best at rock, paper, scissors? Is there actually a strategy to this? And we did this by performing a lab. Now, we selected 2 players from this group to be player 1 and player 2 to play 26 rounds of rock, paper, scissors, and then another to play another 26 rounds, so player 3 and player 4. So there's a lot of different ones, and we calculated that with a spreadsheet. So we recognize a problem, right? Is the following statement a scientific claim, why or why not? The previous outcome of a round of rock, paper, scissors won't have an effect on the next round. Well, yes, it is a scientific claim because there is a test for wrongness. We can go out and see if the previous round affects the next round. Now, we make a hypothesis, write your hypothesis. Do you think the previous outcome of a rock, paper, scissors will or will not have an effect on the next round? So we need to be as specific as possible. So like I would say, yes, it would. I think maybe people, if they win, they tend to do this. If they lose, they tend to do this. Make predictions based on hypothesis, right? So that's sort of the sort of the same thing, like making a prediction. Like if we played this many rounds, if we played this many rounds, this percentage of people would change based on this, right? So that's sort of the difference. Making a prediction is making a prediction about an experiment. So now we can perform an experiment. Every group will perform 52 rounds of rock, paper, scissors, where the outcome of every round is recorded. Identify the independent variable, dependent variable, and 3 constant variables. So the independent variable, the previous round of rock, paper, scissors. The dependent variable, the next round of rock, paper, scissors. Now, constant variables, so you want to keep things the same. So like the reward, right? So if maybe people play differently if there's a reward on the line. Maybe the type of people, right? Maybe like somebody that just learned the game of rock, paper, scissors plays it differently than someone experienced. Who knows? You want to keep maybe the setup the same, right? Best out of 3, best out of 26, whatever. You want to keep everything the same except for what you're measuring and what you're changing. So we did that, and I was able to compile all the data. We look at the bar graph. What is the general pattern for how people play rock, paper, scissors? So this didn't really go with the convention that I thought it would, which is fine because it was just based on the data in this experiment. Consider when people tend to win, they tend to upgrade. When they lose, they tend to downgrade. Not a lot of people play the same thing when they draw. It's kind of when they draw, well, they tend to change. Right? They tend to change what they that didn't win. Great, moving on. Now, was your hypothesis wrong? Did the previous outcome of rock, paper, scissors have an effect on the next round? I would say yes. I would say it does. It does have a psychological effect, whether you win, lose, or draw. And I would say it's because psychologically, we put like, oh, I just lost with this. It's a weak hand. I don't want to play it again. Oh, I just won with this. It's a strong hand. I want to play this again or play something stronger. So formulate a general rule. Formulate a general rule. Come up with the best strategy for playing rock, paper, scissors. That's just filling this out, right? If you won, then your opponent lost. Based on the data, they would most likely do this, then you should do this. So just sort of flow chart based on the data. So this would change depending on what data you have. And what is another scientific claim that could be made using the game of rock, paper, scissors? Then describe an experiment. So this would be like saying different age groups play rock, paper, scissors differently, right? Maybe that is. Maybe a reward affects how people play. If there's $100 on the line, people might play differently than if there wasn't, right? Maybe best out of 3 is different than if you play just one round. Maybe people will play differently. Who knows? Like there's a lot of different things that just come up with an experiment. And if we look at the data on this, there's a research paper that was that some university in China where they did play a lot of rock, paper, scissors, and there was 2 experimental observations. When a player won a round, more often than not, the player chose the same winning element for the next round. When a player lost a round, more often than not, the player chose to avoid the same losing element for the next round. So they came up with this winning strategy. If you win using one element for the next round, go for what element your opponent just lost with in the current round. If you lose using one element for the next round, go for whatever was not called by either of the players in the current round. Now, the data that we got did not seem to suggest that, and the reason why is because we weren't playing for anything. Nobody even knew if they were winning or losing. We just went back there and played a bunch of rounds. So people would mess around and play like maybe 10 rocks in a row, or who knows? Like it was just it really so we could change up this experiment next time to make another experiment. See if people play different. If there was a tournament in the class. So it's just kind of interesting. Like so that doesn't mean it doesn't mean just because our data doesn't fit. Well, it just appears as if people just didn't appear to play the same thing over and over again, and people changed up whether they won or lost, but it didn't. It was almost close. So if you're just playing a bunch of rounds without knowing who's going to win or lose, you just tend to change it up. And the majority of the class threw scissors first round. Why do you think that was? Well, because rock, paper, scissors. It's the last thing you say. So maybe that has an effect. That could be another experiment, right? Maybe if you're silent, people, maybe that first throw is about 1/3. But if you do rock, paper, scissors, maybe it's different than scissors, paper, rock. So who knows? That could be another experiment to do. Do the actions of flipping and spinning a penny affect the percentages of which that penny lands? So if we look at those variables again, it is a scientific claim. We can go out and test this. The independent variable, if do actions of flipping and spinning a penny affect the percentages of which the penny lands? What is being done to the penny? That is what we're changing. That is the independent variable. So the dependent variable is what is being measured, right? We are measuring the percentage that that coin lands on heads or tails. The constant variable, so we want to keep a bunch of things the same. So that'd be the person flipping a penny. The height the penny is flipped. The side the facing is up at the beginning, whether it is flipped at the end or not onto the other hand. And the penny, right? The penny. So lots of things need to remain the same. So in order to keep the penny the same, we had to do a little bit of research to make sure that it has the same weight, same back, composed of the same material. So if you find pennies between 1982 and 2008, they will be composed of the same material, have the same backside, have the same weight. So that's how we kept the penny the same. So in order, we did penny for your thoughts. So we already recognize the problem, right? So that is, hey, what if I spin a penny and flip a penny? Will that have an effect on that? So we make a hypothesis. So like I would say, I think it's going to land tails up more often because I think the Lincoln's head has more mass and it's going to tend to fall that way. So if I make a prediction, right, based on the hypothesis, I would say something like, I would say that I think it's going to land tails up more than 50% if you spin it because of that mass distribution. Now we perform the experiment to test the predictions. We already went over the independent variable, the dependent variable, and the constant variables. So we did this experiment. We flipped the penny 50 times, measured it, spin the penny several times. And so just answer, was your hypothesis wrong? So that sort of depends on your data. Was there significant differences in the percentages when comparing the flipping a penny to spinning a penny? If so, claim why do you think that would be? So remember, for the claim to be scientific, there must be a test for something. So formulate a general rule, come up with a scientific claim. So for the results of this lab, why do you think we got the result? That would explain a lot. Like I thought it was based on the amount of metal, but who knows? That's up to you. And the last one, we didn't get a chance to do this, but it's just a fun thing to do. The probability of landing an American nickel landing on its edge if tossed onto a flat surface is approximately 1 in 6,000 tosses. So if you want to do that, that's kind of fun to try. Could be the first time. Who knows? 1 in 6,000 every single chance. So once again, there is just too much unknown in the universe to take a break from learning. Get out there and question everything.